The future of flight is here, and it's printed in 3 dimensions. Introducing the revolutionary 3D printed fuel nozzle, a marvel of modern engineering that's setting new standards in aerospace technology. Hey everyone, and welcome back to Aero Briefing. Today, we're diving deep into a tiny but mighty component that's completely revolutionizing the world of jet engines, the 3D printed fuel nozzle tip of the CFM International LEAP engine. This isn't just a part, it's a testament to how cutting-edge technology is pushing the boundaries of what's possible in aerospace. So, what exactly does this little marvel do? Well, in a turbofan's combustor, the fuel nozzle tip is responsible for precisely delivering and atomizing fuel into compressed air. Think of it as the ultimate spray painter, ensuring efficient combustion. The CFM LEAP engine, a brilliant collaboration between GE and Safran, uses 18 to 19 of these fuel nozzles in each combustor. Their precision directly impacts everything from engine thrust and emissions to, most importantly, fuel efficiency. And get this, the LEAP engine boasts an impressive 15% better fuel burn than its predecessor, the CFM56. A significant chunk of that improvement, you guessed it, the incredibly complex internal design of this 3D printed fuel nozzle. As Mohammed Etishami, GE's former chief engineer, put it, these tips spray fuel into the combustor and help determine how efficient it is. In essence, this fuel nozzle is the jet engine's fuel injector, meticulously shaping the flame for peak efficiency and minimal emissions. Here's where it gets truly mind-blowing. This single sleek metal part replaced an assembly of 20 individual welded pieces. This consolidation slashed the weight by approximately 25%, and get ready for this, it survived 5 times the fatigue life of the older design. That's not just an improvement, that's a game changer. How do you go from a 20-piece Frankenstein to a single monolithic marvel? The answer lies in additive manufacturing, or 3D printing. Instead of traditional casting or machining, GE redesigned the LEAP nozzle tip as one consolidated part. The journey begins with a detailed 3D CAD model, often optimized using advanced flow simulations and topology optimization software, which basically places material only where it's absolutely needed, minimizing weight while maximizing strength. This digital model is then sliced into hundreds, even thousands, of incredibly thin cross-sectional layers. In the printer, each layer is built by spreading a fine metal superalloy powder and fusing it with a high-energy heat source. GE primarily uses laser powder bed fusion, LPBF machines like the Concept Laser M2 dual laser systems featuring powerful 400 to 1000 watt lasers. They also utilize Electron Beam Melting, EBM machines, which use an electron beam in a vacuum chamber. Each layer is astonishingly thin, around 50 micrometers thinner than a human hair. The machine repeatedly deposits powder and writes the nozzle shape, building the part from the bottom up. As GE aptly explains, it literally grows parts directly from a CAD file. Printing is just the beginning. Once the part emerges from the printer, it undergoes a series of critical post-processing steps. Stress relief annealing and hot isostatic pressing, or HIP, are used to eliminate microscopic pores and normalize the metal's microstructure, making it incredibly robust. Next, support removal and precise machining of critical surfaces ensure tight tolerances. Then comes non-destructive inspection, often via high-resolution CT scanning or X-rays, meticulously checking for any internal defects. Finally, surface finishing through blasting or polishing ensures the nozzle meets rigorous aerodynamic and fit requirements. Each printed tip involves over 3,000 layers, and every single printer must be meticulously calibrated for power, scan speed, and powder spread to consistently meet specifications. GE's Auburn, Alabama Additive Center is a testament to this high-volume production. It was purpose-built with metal 3D printers capable of aerospace-grade precision. They have over 40 printers running in parallel, churning out these nozzles. For instance, the Concept Laser M2 Series 5 with its dual 400-watt or 1-kilowatt fiber lasers builds parts in a 21,000 cubic centimeter chamber, creating the intricate internal channels that make the LEAP tip so efficient. The whole process is continuous. A single nozzle build can take 2 to 3 days, given the thousands of micro layers being fused. And what about the materials? The fuel nozzle tip is crafted from high-temperature superalloys, Early R&D used a cobalt chrome alloy, known for its heat resistance and durability, but for production, GE qualified a nickel-based superalloy, typically Inconel 718, an alloy long used in jet engine hot sections. This material retains its strength at incredible temperatures ranging from 800 to 1000 degrees Celsius, and resists oxidation, making it perfect for the brutal environment of a combustor. The result? This 3D printed tip is an astonishing 5 times more durable in fatigue life than the older multi-piece design, thanks to both the advanced alloy and the elimination of welds. A project of this magnitude isn't the work of one person, it's a symphony of multidisciplinary expertise. Key figures like manufacturing. He assembled a top-notch team including turbine blade expert Josh Mook, who designed the tip's 14 internal channels, and additive pioneer Greg Morris, founder of Morris Technologies, which GE later acquired in 2012. Even French partner Safran engineers collaborated through CFM's joint program. Roughly 100 engineers and technicians initially worked on the nozzle's development, including CAD/design engineers, combustion experts, material scientists, and AM process engineers. By 2018, the Auburn manufacturing site had 230 staff, growing further by 2021. Their roles range from plant leadership, like Andrea McAllister, the GE Auburn plant manager, to additive manufacturing technicians, quality inspectors, and even data and AI specialists. Even after production, aerospace mechanics and technicians are crucial for fitting each tip onto the fuel manifold. Maintenance shops now use special maintenance carts to clean and inspect these AM nozzles, requiring engine technicians to learn new skills for handling and inspecting these 3D printed parts. It's a truly collaborative effort across every stage of the life cycle. This entire process is underpinned by advanced digital technologies. All nozzle designs begin in CAD and often leverage generative design or topology optimization software to create the lightest, strongest structure. During printing, machines log gigabytes of sensor data, laser power, temperature, layer images, creating a rich data set for big data analytics and AI. While specific details for the LEAP nozzle are proprietary, GE's additive group has invested heavily in data platforms to monitor part quality in real time. Machine learning algorithms can analyze past prints to predict and even correct defects. Imagine the power of knowing a potential issue before it even happens. Predictive maintenance of the printers themselves is another big data use case, allowing engineers to schedule service before a machine fails. And looking to the future, augmented reality, AR, and other Industry 4.0 tools are set to play an even bigger role. AR headsets could allow technicians to see overlaid instructions on real parts, visualizing internal flow passages during inspection, or guiding the assembly of the nozzle into the fuel manifold. The trend is clear: AI, machine vision, and AR will continue to streamline 3D printing workflows in aviation factories, leading to even greater efficiency and precision. So, what's the payoff for all this innovation? It's simply massive. Part consolidation eliminated around 20 parts per nozzle tip, making it a single piece. This drastically cuts assembly time and potential failure points. The printed nozzle tip is approximately 25% lighter than the older design, contributing to slight efficiency gains. On an engine scale, the fuel burn improvement is the big LEAP engines are about 15% more fuel efficient than CFM 56 engines. Over an aircraft's life, that saves millions of gallons of jet fuel and significantly cuts CO2 emissions. Manufacturing costs have plummeted by about 30% per nozzle tip, thanks to less machining, welding, minimal scrap, and simpler inventory. GE even found that metal 3D printing can compete on cost with traditional casting. And as for durability, the monolithic tip lasts an incredible 5 times longer, reducing replacement frequency. Lead times have shrunk from months to weeks, enabling faster design iterations in production. These numbers are staggering, backed by GE and CFM data, and they unequivocally demonstrate why the 3D printed LEAP nozzle is a true game changer for aviation manufacturing. This breakthrough wasn't an overnight success. Around 2003, GE combustion engineers, led by Marie McMasters, designed the LEAP nozzle's complex internal fuel passages. The problem? Conventional casting couldn't create it. Designers tried to cast it 8 times and we failed every time. Then, from 2007 to 2012, GE's newly acquired Morris Technologies lab, spearheaded by Greg Morris, secretly worked on printed prototypes. By 2005 they had 3D printed a test injector from cobalt chrome, proving the geometry was feasible. By 2012, GE had developed robust print parameters to mass-produce all 19 fuel injectors per engine using additive manufacturing. This vision led to GE acquiring Morris Technologies in 2012, founding GE Additive. The LEAP engine was certified by the FAA EASA in 2015. That same summer, GE opened its 300,000 square foot Auburn, Alabama Additive Center, specifically for printing these fuel nozzles. The first 3 D-printed LEAP nozzles entered service on a 320 Neo jets in late 2016. Production has ramped up steadily ever since. Auburn went from a handful of printers to over 40 machines by 2018, producing 30,000 tips. And in 2021, Auburn celebrated the production of its 100,000th printed nozzle tip, at a time when LEAP engines had already logged over 10 million flight hours. Today, every LEAP engine delivered uses these additively manufactured tips. The Auburn plant now employs around 300 advanced manufacturing staff and continues to expand, working closely with local universities on AM research. The 3D printed LEAP fuel nozzle tip is more than just a single part. It's a shining example of how additive manufacturing is fundamentally transforming aerospace. A component once considered too complex to manufacture is now a single, lighter, tougher, and more cost-effective printed piece. It's a testament to the convergence of brilliant design, advanced machinery, innovative materials, and a dedicated team of engineers and scientists. Thanks to this innovation, airlines are seeing lower fuel burn and reduced maintenance costs, while engine manufacturers are embracing a new, digitally driven factory paradigm. As leaders at GE Additive say, this tiny, walnut-sized nozzle tip didn't just revolutionize one part, it launched an entire business unit and proved that metal 3D printing can indeed work at scale. This incredible success story continues to evolve, with AI-driven optimization and even more efficient designs on the horizon. The future of flight is truly being printed one layer at a time. What other breakthroughs in manufacturing are you excited to see? Let us know in the comments below. Don't forget to like this video and subscribe for more deep dives into the world of science and technology.